Welcome to our exploration of ultrasonic and vibration welding, two efficient joining technologies that harness mechanical vibrations to generate frictional heat and create strong bonds between materials. These methods are particularly favored for their speed, cleanliness, and versatility in joining a wide range of materials, including both similar and dissimilar types. Common applications span across various industries, such as automotive, aerospace, medical, and electronics. Ultrasonic welding utilizes high-frequency vibrations, typically between 15 and 40 kilohertz, applied through a tool called a sonotrode, which concentrates the energy at the joint interface. The localized heat generated melts the materials, creating a solid-state weld upon cooling. On the other hand, vibration welding employs lower-frequency vibrations, usually ranging from 100 to 300 hertz. Here, the parts are held together under pressure and subjected to lateral vibrations, melting the materials at the interface to fuse together. These welding techniques not only offer numerous advantages over conventional methods, but are also environmentally friendly, as they don't require adhesives, solvents, or consumables, providing high-quality welds with minimal distortion, making them ideal for intricate and delicate components. Diving deeper into the mechanisms and applications across industries, let's start with ultrasonic welding. In this method, the sonotrode transmits high-frequency vibrations to the parts being joined. This focused energy creates localized heat at the interface due to molecular friction, melting the materials and, with the application of pressure, forging a strong bond as they cool and solidify. This technique is particularly suited for thermoplastic materials, but can also be used for metals and some composites. Conversely, vibration welding utilizes lower frequency, linear vibrations to generate heat. The parts are held together under pressure and vibrated laterally, creating friction at the interface, leading to localized melting and subsequent fusion upon cooling. Vibration welding is often preferred for larger parts and materials with higher melting points, such as thermosets and some metals. Both techniques find extensive applications in various sectors. In the automotive industry, they are instrumental in assembling components like dashboards, door panels, and lighting systems, and are crucial in manufacturing parts for electric vehicles, including battery packs and power electronics. The aerospace industry benefits from these technologies in joining lightweight materials like aluminum and composites, contributing to fuel efficiency. Additionally, medical devices such as catheters, filters, and implants often rely on ultrasonic welding for its precision and ability to create hermetic seals. One of the significant advantages of ultrasonic and vibration welding is their capability to join dissimilar materials, which expands design possibilities and is particularly valuable in industries like electronics and automotive, where integrating components with different properties is crucial. For instance, ultrasonic welding can effectively join metals to plastics, a common requirement in electronic assemblies. These techniques offer several advantages when joining dissimilar materials. Firstly, they eliminate the need for adhesives or fluxes, which can be incompatible with certain material combinations. Secondly, they produce highly localized heat, minimizing the risk of thermal degradation or distortion of sensitive materials. This localized heating also allows for precise control over the weld, resulting in stronger and more aesthetically pleasing joints. However, challenges exist when using these methods for dissimilar materials. One significant hurdle is the difference in melting points and thermal conductivities of the materials being joined, which can lead to uneven heating and consequently weak or incomplete welds. Careful selection of process parameters, including amplitude, pressure, and weld time, is crucial to mitigate this challenge. Another challenge is the potential for damage to sensitive components, especially in electronic applications. The high-frequency vibrations used in ultrasonic welding can damage delicate circuitry or components sensitive to mechanical stress. Therefore, proper shielding and isolation techniques are essential to protect sensitive elements during the welding process. Ultrasonic and vibration welding are eco-friendly joining methods. They align with the principles of sustainable manufacturing, making them increasingly important in a world striving for reduced environmental impact. Their contribution to sustainability stems from several factors. Firstly, these techniques are energy efficient. They require significantly less energy than traditional welding methods, as they generate heat only at the localized joint interface. This targeted energy application translates into lower overall energy consumption during the manufacturing process. Secondly, they eliminate the need for consumables like adhesives, solvents, or fillers. These substances often have harmful volatile organic compounds, VOCs, that contribute to air pollution. By eliminating their use, ultrasonic and vibration welding contribute to a cleaner and healthier working environment. Furthermore, these methods minimize waste generation. They produce precise and clean welds, reducing the need for post-weld finishing or rework, which typically generate waste materials. The durability of the welds also contributes to the longevity of the products, reducing the frequency of replacements and associated waste. The future of ultrasonic and vibration welding appears promising, driven by the increasing demand for efficient and sustainable manufacturing processes. Ongoing research and development efforts focus on expanding their applicability to a wider range of materials and component geometries. Recent research in ultrasonic and vibration welding focuses on optimizing process parameters for specific material combinations and applications. For instance, studies explore the use of advanced materials like carbon fiber reinforced polymers, CFRP, in aerospace and automotive applications. These lightweight and high-strength materials pose unique challenges for joining, and researchers are developing specialized ultrasonic and vibration welding techniques to address these challenges effectively. One notable case study involves the application of ultrasonic welding in the manufacturing of electric vehicle batteries. Researchers are exploring ways to use this technique for joining battery cells and components, ensuring efficient electrical connections and structural integrity. The ability of ultrasonic welding to create hermetic seals is particularly crucial in battery applications to prevent leakage and enhance safety. In the medical device industry, recent advancements focus on miniaturizing ultrasonic welding systems to join intricate components used in catheters and implants. Researchers are also investigating the biocompatibility of these welding methods to ensure patient safety. The ability to create strong and reliable joints in biocompatible materials makes ultrasonic and vibration welding highly suitable for medical device manufacturing. These case studies highlight the continuous evolution and growing significance of ultrasonic and vibration welding in various industries. The ongoing research and development efforts demonstrate the commitment to refining these techniques and expanding their capabilities to meet the evolving demands of modern manufacturing. Ultrasonic and vibration welding are efficient, precise, and environmentally friendly joining technologies. They have become indispensable in numerous industries, including automotive, aerospace, electronics, and medical devices. Their ability to join both similar and dissimilar materials, combined with their efficiency and minimal environmental impact, makes them vital for modern manufacturing. These technologies offer significant advantages over traditional welding methods, including speed, cleanliness, and the ability to join delicate components with minimal distortion. They are particularly well suited for joining thermoplastic materials, but advancements in technology are expanding their applicability to metals, ceramics, and composites. As industries strive for sustainability and reduced environmental impact, the importance of ultrasonic and vibration welding continues to grow. These technologies align with the principles of green manufacturing by reducing energy consumption, eliminating harmful consumables, and minimizing waste generation. As research and development efforts continue to push the boundaries of these techniques, we can expect even wider adoption and innovative applications in the future.